is that remember that you are talking about the Ohm's law, and we talking about the resistance, right? That we saying that the ratio between the voltage and the current running through this resistor is uh, is constant, right? If you measure, this is experimental results, this is constants. The other thing that we want to talk is actually that if we consider like any kind of conductor, for example a cylindrical conductor with a given length L and a given area A, this ratio, the resistance is always proportional to the ratio between, is directly proportional between the ratio between this length and the area. In other words, we can say that this resistance is directly proportional to the length of this conductor, right? And inversely proportional to the area. We know this since high school. I can show here for you some simulations from the University of Colorado. As you can see here, for example, this is resistivity. Resistivity is a property of the material, remember? Resistance is a property of the object itself, but this depends on the material that the wires is made, for example. And if you increase the length, look, what is going to happen is actually you also increase the resistance. If you decrease the length, you are going to decrease the resistance. So this is a classic way of saying that you have two quantities that are directly proportional. That means that the resistance is directly proportional to the length. And on the other hand, if I increase the area, what happens is actually that we decrease the resistance, and if I decrease the area, is going to the resistance of is going to be increased. So this is what you call one two. This is when two physical quantities have this kind of relationship. You say, mathematically speaking, right? That they are inversely proportional. But we know this since um, high school. Nothing new here. Oh my. Dun, dun. Let's go here. Just continuing here, guys. We know this from high school. I can actually show you here that, for example, I got this picture from LibreTexts, right, guys? For any kind of resistor, right? If you wanna know its resistance, you can remember that you have actually four bands, four bands with different colors in this resistor, and every single band represents something. The first band right here is the first digit, so you have this is the second digit, third digit, and fourth digit. Sorry, first, second, this is the multiplier. Sorry guys, so this is the first digit, this is the second digit, the one here, the third band means the multiplier, and the last one means the tolerance. You have two tolerance only, so it's very easy to know if each one is the first digit and second digit and so on, because for the tolerance we have only two colors. We have gold and silver, and that means for gold you have 5% tolerance, and for silver you have 10% tolerance. And the other three bands, then is easy. First one, first digit, for example in this case red, you go here, red, that means 2. Black, here second digit means 0, so that means 2, 0. And The third band is the multiplier. In this case is green, means 10 to 5. So for this particular resistor that you have on your screen, you have the resistance is going to be 20 times 10 to 5 ohms, with 10% of tolerance. If you want to write some other way, this is going to be 2 mega ohms with again 0.2 mega ohms of a tolerance. Again, guys, let's just to finish this part here. Let's see. You have three figures here, right? You have these 3 cylindrical copper conductors along with their faces, areas, and length, and you want to know. And the problem is asking us to rank these according to their resistance as well. So for the first one, let's see, we know that the resistance, this is the same material for these guys, so saying this copper, this resistivity of copper divided by this length A. For the second one is the same material, the length is here is 1.5 L divided by A over 2, so that means that we are going to have this is going to be 3 LA, so that means that for the one in the center you're going to have 3 times the resistance of the first one, and for these guys, for this guy here, you can do the same, right? You can do by yourself. You have to use the same material, the length here, divide by this area, and you can reach your own conclusion here. You can actually study those ratios. That again, this is what you used to do in high school, right, guys? Just going here and where is it, analyzing this kind of proportions here. What happens when we have increase in length and increase in area, or decrease in area, and so on. Okay, you can play with this by yourself. Let's go, let's move. Another thing that is important to mention, that since the electrons move inside the wires, and when this happens, the electrons generate energy, and this energy is actually dissipated. Some part of this energy is dissipated through heat, and then this heat is going to actually change the resistivity of the wires, of the material that compose the wire. And we know for very long that, of course, this is very important to say, within certain limits, that this increase or decrease, this increase in resistance, right, it depends on the temperature. So you're going to have like a one increase in the resistance of the wires depending on the temperature. So, but this is very easy, it's not complicated. We're going to have some very complicated phenomena in nature, but this one is not complicated at all. This is very easy because this is linear. It's going to be pretty much linear for within some reasonable limits. You guys can read about that, and what it's saying is right that if you have one increase in temperature, what you're going to have is just a linear increase, as you can see in the graph here, in this area here. You're going to have one linear increase in the resistance, and this is proportional to this variation in temperature. And the coefficient of temperature here, I put, guys, right here in this page, this temperature coefficient alpha, then the is right here. You can see how this goes, and this is something similar to what we see, for example, in dilatations in solids, right, caused by temperature. So you have it's not impervious, so something is going to happen. So the changes in temperature, they will affect physical properties of the material, not only physical properties but dimensions as well. So this is well known. As I mentioned before, this is Ohm's law, Ohm's first law. That means that the voltage and the current in one ohmic component is going to be, they're going to be proportional. And you can see this, for example, if you analyze this problem here, right, the problem is giving us two tables, right, two devices with a correspondence between the voltages and currents. Is missing the units here, I don't know, very bad. Physicists, we don't feel so comfortable without units, so let's put the units here. This is going to be volts, and this amperes. The last example that I'm going to do today, guys, I'm going to probably coming give you a summary of this next class again, because this was very fast class. If you come here, what you can see, if you analyze, for example, the differences in voltages here, if you calculate this difference here, this is going to be 1 volt. For the next two values, again, this is going to be 1 volt. And here I'm going to have this difference here is going to be 2.25. For the next two values, again, we have the same amperes. And if you calculate this ratio here, you're going to see that this is going to be exactly the same. So in both cases, the resistance, right, this ratio, since we know that we have, if you have these pairs, they should fit like a line, straight line, and the resistance is going to be the angular coefficient of this straight line. As you can see here, if you plot the first values here, also this is the analytic method, right, since the angular coefficient should be the same, but geometrically, if you plot those points here, you are going to see that those 3 points, they fall on a straight line clearly. The other 2 points here is not the same. Clearly you can see here, let me erase this. You can see that the difference is stay the same, right? This is going to be 1 volt between the values here, but for this case here, for the first one, this is going to be 0.7 amperes, and this difference here is going to be 0.6 ampere. So this difference is actually different, And if you calculate the ratio, right, the resistance here between these, for the first one, this is going to be 10/7 ohms, and for the second case, this is going to be 5/3 of ohm, and this definitely not the same, those are different. So this is ohmic, and this definitely not non-ohmic. And again, if you actually if we plot those points, you can see that clearly those points, they do not fall in a line. Even if I try to fit a line there, right, with those inclinations is completely different, so they do not correspond to those points at all. So that's, we cannot fit. Guys, that's all for today. I hope we enjoy the lecture. We still have to talk about a little bit about power, but it's nothing new. We learn about power in high school as well, right? It's just a way of talking about how work is done in one electric circuit, or how like a particular source can actually supply work for a given circuit. Okay, my friends, so talk to you next week, and you can start doing uh, the homeworks. Okay.